Welcome. This video here will be a quick example of how to calculate shear stresses due to torque, and also how to calculate twisting angles due to the torque and twisting angle of a section here somewhere along this shaft. So we're giving this shaft, it's 14 feet long, made up of two different segments here. AB has a diameter of 6 inches or radius of 3 inches. BC has a radius of 2 inches, and we have two torque loads here, 5 kip-foot and 20 kip-foot. This shaft here is made of steel, so its shear modulus or modulus of rigidity is 12,000 KSI. The problem here asks for the maximum shear stress in the shaft. Anywhere along the shaft, we want to look for, searching for here, the maximum shear stress that develops in the whole shaft, and then the rotation of point C relative to its original position. So the first thing we need to do here is statics. So this is a shaft fixed at this fixed support at A. And to figure out what's the value of TA, I will need to put a positive direction for my calculations here. So I'll assume it's going away from the support, and this double arrow here is just a way to represent the direction of a moment using an arrow, a straight arrow. So it's kind of the bent arrow, and the straight arrow will give you more sense of feeling the positive direction here of the moment torque. So if you do summation of moment torques, the sum of T is equal to 0. We'll not do that in detail, but you can see here that 5 kip-foot is in the positive, so it's positive 5, and then negative 20. This will mean that's negative 15, the resultant of these two torques. And to have equilibrium, you have to have a positive 15, which is TA, countering them, so you have a case of equilibrium. Once you figure out the reaction, now you can draw the internal torque diagram. So I'm presenting here the torque, and you start here, and we have the positive and negative, and your units here are kip-foot. If I want to follow that positive direction that I had, which is an arrow going to the right, that's going out of the surface when I look from the right of the shaft. So I will start from the right of the shaft. So if I want to follow my positive direction that I set in the beginning, I will need to start my drawing the diagram from the right of the shaft, because the arrow is going to the right. I can start from the left, but my positive will be the other way. So if I start from point C, I will hit here 5 kip-foot, and that will be in the positive direction. So I'm starting from point C, and then I will, this internal torque will be the same because there is no change, no loads between B and C. And then when I hit B, I will hit 20 kip, which is going in the negative direction. So that will be causing a drop of 20, which means from 5, I'll be at negative 15. So that's at point B. And then I will keep going straight until I hit the support, and now TA is actually in the positive direction, so I move from negative 15 with a delta of positive 15. That will bring me to 0. So that's kind of the case where I know that I have a correct, a right internal force diagram, because I end up at 0, which is the equilibrium. So now I know that tau, or torque, if I call this torque A, B, because this is point A, this is equal to negative 15, and torque BC is equal to positive 15. So now the part A, I need to find the maximum shear stress in the shaft. We learned that tau max is equal to TC over J, but this tau max is only kind of, we're focused on only one section. Now we need to consider multiple sections along this whole shaft, and try to think where's really the critical section here. So I have two homogeneous segments of that shaft, segment AB and BC. So if I look at segment AB, TAB is large, is 15 kip foot, but also the section there is a little beefy, right? It's a 3-inch radius. And compared to segment BC, I have little torque, but I have also little section. So when I have a bigger section, that translates into a bigger J, the polar moment of inertia, which reduces the torque. Even if I have a bigger, it reduces the shear stress tau, even if I have a large T torque value. So I don't have here a clear cut. I don't have a clear direction. Where is actually the critical section? So I have to now to consider both possible sections at any point between A and B and any point between B and C. And now TAB slash max at AB section is equal to TAB, so tau AB is equal to TAB, CAB, so within this section, the largest shear stress will develop at the outer points of that section. So now I'm not considering rho, I'm considering C. So rho here is equal to C. So CAB divided by JAB, and similar thing for tau BC. I want to calculate here the moment of polar moment of inertia. So JAB and JBC is pi, the radius to the power 4/2. So I have here, we can see that the polar moment of inertia for any point, the sections at AB are larger because you have a larger radius. Now if I calculate tau AB using T, C, and J values, that will be the value of the shear stress, 4.25 KSI. And if I want to calculate tau BC using its corresponding values, that will be 4.78 KSI. You see it's pretty close call here, but from the values that I calculated, not being based on guessing, the critical section will be a section between points B and C, and the maximum shear stress will equal to 4.78 KSI. Pay attention here, one thing, to the conversion of units. So 15 for tau AB, the torque is 15 kip foot. So, and my units here, I wanted to make them all in inches, so I multiply by 12 inches per foot, and then radius is 3 inches. So pay attention to the units here. Part B is finding the twisting angle or the rotation of C here with respect to its initial conditions. That's basically the twisting angle at C. And I want to clarify here, this twisting angle at C, of section at C, I will relate it to a fixed point that I know it will not move. So A is fixed, so I will say phi C, its rotation to its original position or condition, is equal to its rotation relative to any point in cross section A. So I'll call it phi C A. And that phi CA that step of saying phi C is equal to phi CA. Now I can break down this segment or length CA into two segments. So it will be CA is CB plus BA. And the accumulation of twisting along these between these two segments will give me the twisting of point or section C. And we know from the previous video that phi is equal to T L over J G. All the two sections will have different values for T, L, and J, but the whole shaft is made out of steel, so I'll call this is just G. And we will plug in the values. Now I have everything given. I found the internal forces, and now one thing you have to pay attention to here is when you pull the values of TAB and TBC from the internal torque diagram, get them with their signs. So TAB is negative 15, and the length here is 9 foot. Pay attention to the units, conversion of units from feet to inches. And then if I calculate here phi BA, pay attention to that torque BA here is positive. So I plug in positive 5 kip foot. And the individual value of these twisting angles, the first one is a negative one, the other one is positive. So the net here will be negative. And remember, the units of twisting angles are in radians. So it's negative 788 10 to the power negative 6 radians. Or if I multiply by 180 over pi, that will give me the degrees for the angle phi c. Now I want to feel where's actually this section going. Is it twisting clockwise or twisting counterclockwise? It depends on the direction you assume to be positive that you use to develop the internal moment or internal torque diagram. So if I assume positive to be going counterclockwise when I look from the right to the shaft, negative twisting angle means it's actually clockwise. So the twisting direction here, I can say it's a clockwise. It's opposite to the positive direction I assumed in the beginning, and I used it to add values of torques and their twisting angles. So very nice problem here showing how to calculate shear stresses from torques on a shaft, figuring out the maximum of that shear stress along the shaft length. Sometimes you have a clear call for a critical section, sometimes not, so you have to calculate for all possible sections. And we'll see how to accumulate twisting angles over the length by considering the homogeneous segments of that length with the same T, L, and J values. And pay attention to figuring out the direction of the twist, clockwise, counterclockwise, based on the direction, positive direction that you considered in the beginning of the problem. Thank you and take care.